Okay, so I'll go ahead and share my screen. Oh, whoops. Gosh. Is it? Okay, so let me just get situated with this thing from Zoom. Okay. All right. Hi, everyone. Thank you for joining us today. So the title of my talk, Doing Things in VR, Designing 3D User Interfaces and Using Our Perceptual Limitation to Enhance Our Interaction. And currently I'm a visiting associate professor in the Atlas Institute here at CU Boulder. So let me go ahead and get into it. So one of the reasons why I'm giving this talk is because I really want to kind of just give a flavor of some of the research that I do with the hopes that maybe that could tie into something, some work that someone else is doing, or maybe that could at least spark some interest to kind of meet with me and discuss and brainstorm other ideas and things like that. So I think of, a honeybee that's going around, and the more that the honeybee kind of flies around and gathers more pollen and, kind of gets it all over himself and then kind of flies around to the next flower, that cross-pollination of research is what I'm trying to get at. So I would really like to cross-pollinate with some of you. Okay, so who am I? So you're probably wondering, who's this lady talking about bees when her talk's not even about bees? So I could answer this question in a number of different ways, one of which is kind of what is my academic background. And as Ava mentioned in the beginning, I studied my undergraduate degrees in computer science and studio arts at Duquesne University. And then I went on to UNC Charlotte to study my master's and PhD under the advisement of Larry Hodges. And so at that point is when I started working in virtual reality and some other types of work as well. And then I went on to, in 2008, I went on to Clemson University, where I held a postdoctoral fellowship position. And in 2010 is when I joined the University of Wyoming, and I've been there ever since. And this year, I'm here at CU Boulder for the year. So I really want to take advantage of my time here. So that's kind of my academic background. Another way to answer this is kind of what is my, if you would, my, I guess it's still academic background, but kind of what makes me who I am and why my research is kind of the way it is. So I do have a background in both computer science and studio and digital arts. And mostly the reason is because I really love both fields. And so I couldn't decide, so I just pursued both. And, but it's led me to my research and what I do now in virtual and augmented mixed reality. Which is deeply rooted in computer graphics and as well as human-computer interaction. And so I'm very curious as to how we can do tasks better in VR environments and mixed reality environments. And that kind of started with maybe that mix of computing and studio and digital arts that I had. So one of the things that when I was learning how to perform digital modeling, it was very frustrating in the sense that at the time, there were only a division of the various axes and how you would scale the different models and things like that. And at some point, I asked myself, well, why can't I just digitally model the way I would real clay? Why couldn't I mold and squish and squash the clay like I did in the real world? And so I think even then, early on, I had this curiosity of how can we, better our tasks, or how can we do tasks better in these kinds of 3D environments? But then not just better, but maybe different ways of doing things in these VR environments or 3D environments can lend themselves to other aspects, not just, oh, what's the most efficient way? And spending some time studying for my PhD at UNC Charlotte, there was a core visualization group there. So some of that cross-pollination happened as well. And so some of my earlier career, I looked at interaction techniques for volumetric visualizations and how you could apply some of the foundational techniques for VR to these kind of immersive visualizations. So that's just kind of a little bit about my background, just to kind of give you an idea of where I'm coming from. Okay, so let's talk a little bit about 3D user interaction. And so we think about 3D user interaction. We can look back at one of the first virtual reality head-mounted displays, and actually was an augmented reality display because it was an optical see-through display. So this is Ivan Sutherland testing out his new device here. And the graphics were kind of crude, but it was really great because you could see the graphics overlaid the real world, and you can be more immersed in the environment. He talks about the virtual reality display as being a window into the virtual world. And so then we ask ourselves, well, how do we interact with that window into the virtual world? And even early on, Ivan was thinking about this with his light pen. And so started developing some techniques for this light pen. I'll just show you. So I would consider this a 3D interaction or a 3D device and a 3D interaction technique, because although it's a 2D display, the action or interaction is 3D. So there are a number of ways you could describe that being, okay, you might spatially interact physically, or you might spatially interact virtually, and then you might do both. So you might spatially interact physically and virtually. So it's kind of covering that determination. Okay. So some of the early 3D techniques, and this definitely doesn't, this just covers a very few, and probably ones that you've heard of, being the ray casting technique or Homer technique for selection, or pointing technique for navigation. The reason I mention these is because even now, what are we doing with the commercial joysticks and controllers? Some of these techniques have been implemented almost like a standard, but not fully a standard. And so you can raycast in the environment, you can teleport, things like that. But we're still a lot of ways behind in what we need to work on and accomplish in terms of understanding how we can better interact in 3D and how we can understand our behaviors in the VR environment. And so we can look back to some of the early interaction, but I'm just illustrating this in the sense that we have not gotten much further Not to discount a lot of the body of work that has been done to date. There has been a number of really good research in 3D UI. I think the point that I'm making is we still have a long way to go. And so let me talk a little bit about some of the foundations of 3D user interaction. And so we could consider these some of the universal interaction techniques. But I think they come from a standpoint of efficiency in applications. And I think we can extend these beyond that to more tasks in the environment to be more creative and do more things in the environment. But let's talk about these. So you have selection, and the idea of selection is very similar to 2D interaction in that you want to be able to identify an object to do something with it later. So whether that's a ray casting technique, you intersect with it, whether that's a grabbing technique, doing that in the virtual environment can be classified as a selection technique. Then in manipulation, we want to be able to take the object that we've selected and we want to maybe translate it. So we want to move it along change the position along X, Y, or Z in the coordinate system. And we need a technique to do that. And so you have both the 3D UI, you have maybe various devices that you can complete these tasks with, and then you might have various 3D interaction techniques that you will complete these tasks with. And then the next one is navigation, and navigation can be broken up into two parts. One is the motor component of navigation, which is, okay, if we have point A and point B, how do we actually get from point A to point B? For example, we can teleport from point A to point B. We can incorporate some steering techniques while pointing and move from point A to point B. Then the next part is wayfinding, which is an important component of navigation, and that's the cognitive component, or rather, what are the things in the environment that help us and give us clues to how to get from point A to point B. And so that could be breadcrumbs in the environment. Yes, that's a technique. That could be various landmarks. That could be cues that are giving you maybe ambient cues. They're giving you, how close you are to the end of the environment or things like that. And then system control is kind of the catch-all for everything left, mostly buttons and widgets, things like that. Things that you would use in the environment that wouldn't be really classified as selection or navigation. But I really think there might be another category to this. I'm not quite sure what that category would be, but other things that you would do in the environment that are maybe more creative or maybe don't lead to selecting an object, manipulating it, things like that. Okay, so let's get to some of the challenges. So if we look at the foundation, so we want to select objects, we want to manipulate them, we want to navigate in the virtual environment. There's a lot of different challenges why interacting in 3D user interfaces is hard. And so I'm going to pop out of here and go to different slide deck for a second. There we go. All right, there we go. Okay, so within these challenges, let me kind of talk about what some of those challenges are, and then I can talk about some of those challenges. How can we actually use that to our advantage to interact better in the environment? So let's say we have this setup where we're maybe physically walking around the space. We have a VR head-mounted display that we can see a VR environment. And typically we can add tracking capabilities to be able to either track our head so that we can update our view within the environment. We can track our hands. We can move about the environment as we naturally would in the real world.
Hey, Amy.
Yes.
Your slides are really zoomed in. So we're
Oh.
seeing just a midsection of them.
Oh, weird. Thanks for letting me know. I'm not seeing that on my end.
Oh, now it looks better.
Oh, now it's better?
Yeah.
Okay. All right. I don't know what happened there. Okay, so the idea is that we can interact in the VR environment similar to the way we would in the real world. So you would think, oh, well, easy peasy. That's just like how we interact in the real world. Why is it so difficult? And there are a number of reasons. And one of which is that although we can track position and orientation of your head, of your hands, you know, in theory, we could put trackers all over your body and track your whole body, or using computer vision techniques, track your whole body. Even though we can do that, sometimes we're limited by the degrees of freedom or even the fact that we're providing spatial input. So let me talk about degrees of freedom. So degrees of freedom is, if we go back to position orientation, we can see that we can change translation. So we can change position in X or in Y or in Z. So that would be considered 3 degrees of freedom. And then we can also rotate around X, Y, or Z. And so that's another 3 degrees of freedom. So combined, that's 6 degrees of freedom. And if we have some tracking capabilities that allow us to move or track joints in 6 degrees of freedom, we still might have some areas which we cannot necessarily interact with full 6 degrees of freedom. We might have input device or trackers that limit our degrees of freedom as well. So maybe we have to compensate that with other techniques. And it's not necessarily a bad thing. So there's actually some research that shows limiting our degrees of freedom can help us perform better in the 3D environment. So, but in terms of fully understanding how we can utilize those, we still need to learn a lot. And the other aspect is that you're looking at the screen that's kind of attached to your face, and how we're focusing on that screen can change based on a number of reasons. Could be the optics, it could be how the offset in terms of what you're looking at in the VR environment setup. There could be a number of reasons. And so we might have this spatial offset between what we're doing in the real world and what we're doing in the virtual world that makes it difficult. Okay, so another issue is where in traditional desktop displays, we might interact using a keyboard and mouse. Of course, there's a number of other ways that we can interact. But the point being is, typically in this kind of setup, you have physical constraints of the desk that allow you to kind of leverage that to be more precise, to rest your hand. And in the VR environment, if we kind of go back to this view of our interaction, we don't necessarily have those types of physical constraints. Sure, you can maybe put some props in the environment, some other aspects in the environment that can give you leverage, but as a default, there's not. And so being able to be precise in a spatial interaction can be difficult. And so finding or developing techniques that can help us with that, with the lack of physical constraints, can be useful. Okay. Another problem in the 3D environments are that our layout is just spatially more complex than in, let's say, a 2D desktop display. We have so much more information that we can display, and how we display that information and how we interact with that information can be challenging to the designers, as well as once you have your interaction technique, once you have your device, once you have your layout, those combinations can be useful, or they can be challenging. And you could kind of mimic things that you have in traditional displays, or you might hide things within the VR environment, such as prop-based menus and widgets and things like that, where you kind of tuck them away and pull them out when you're ready to use them. A really great consumer example is the tilt brush, where you can pull out the menu from your joystick when you're ready to change the color, and put it back in when you're painting. Okay. So if we go back to thinking about some of these challenges, just in this picture that I've chosen, as you're interacting, you can actually have more fatigue caused to your body. And there's some of you may or may not be aware of this phenomenon called gorilla arm, where you interact so much, or your arm is kind of in this position for so long, and you're awkwardly reaching for things that you become sore within your shoulder. And I've actually had this, I haven't had it, but in one of my studies, one of the participants started getting fatigue in their arms from what we were studying with some bimanual interaction techniques. In any case, so it's important to think about how we can reduce fatigue, but still kind of leverage, in some cases, that natural movement of kind of reaching and grasping and things like that. Okay, so I also talked about how we see things in the environment. So it's not as simple as you think that, oh, I can see things in the head-mounted display, they kind of look like the real world, it's all fine and dandy, I can see things like I do in the real world. There's an interesting problem that as you're looking at the screen, your eyes are not only focusing physically on the physical display itself, but they're also converging on the object in the distance in the 3D environment. So we can look at this, and as your eyes are focusing back and forth, can cause a lot of strain on your eyes and how you also perceive objects in the virtual environment. So if we look at another issue, which is how we might perceive objects in the virtual environment, we can actually manipulate our perception of objects given the visual cues in the environment. So let's say, as a default, we can have stereoscopic pairs and be able to see depth in the environment. But let's say we don't have anything in the environment to give us any other cues but a cube. Right, so we're just looking at this cube. Now we might add some shading to that cube to give it some depth, and we can tell that it's a three-dimensional cube. Maybe we add some lighting in the environment that will give it some shadows and things like that. Maybe we add some relative objects that give us some idea of the relationship comparison between objects. Maybe even some occlusion cues where we say, okay, there's some objects in front of other objects. I can kind of get an idea of more depth information now. And then maybe we even give perceptual cues that can give us more information. And now all of a sudden we're starting to kind of piece together what a virtual environment might be. But our vision, although these kind of cues can help us determine what is the depth information in the virtual environment, they can also hinder our interaction. So if a particular object is maybe more transparent and it's kind of taking away from some of those depth cues, or even our display itself can affect how we perceive distances in the environment. So there's a number of research where distance estimation is kind of skewed when looking at environments through the head-mounted display. We might perceive objects differently based on what kind of rendering is in the environment. So there's a number of reasons why some of the graphical cues might be helping us and some of the graphical cues might be working against us to hinder or to reduce our performance in interacting using 3D user interface techniques. Okay, based on that, let's say we wanted to go ahead and select that object in the environment, and we wanted to kind of manipulate it and do something with it. So we want to look at, well, how can we maybe use some of these perceptual cues to facilitate our interaction and not just look at it in the negative way. So a lot of you may or may not be familiar with some various illusions, perceptual illusions. This particular one is the Ebbinghaus illusion. And what the Ebbinghaus illusion says that if we have disks around another object, we might perceive that object as larger or smaller based on the surrounding inducers for that object. So let's say the object on the left, the surrounding inducers are larger. So we might perceive that middle object as being larger, or excuse me, the surrounding inducers are smaller and we might perceive that object as larger. And then on the right here, our surrounding inducers are larger, so we might perceive that center object as being smaller. And so what this kind of looks like as we manipulate the surrounding objects, I don't know if you can see some of that, but it changes our perception of that object in the middle in terms of size. So why is this important? Well, as it turns out, when we're in the real world, when we're reaching to grasp an object, we don't consciously do this, but we actually have this perception action process where we see the object that we want to grasp, and our brain does this planning step where we're saying, okay, how are we going to actually, what's the path that we're going to take to reach that object, and then what fine adjustments we're going to make when we actually grasp the object. And this is important related to the Ebbinghaus illusion, because one of the things that we were curious about is if you have these inducers around an object, can that change how you're planning those planning steps in terms of reaching the grasp of that object? And you know, as far as you perceive the size, is that going to change how you're adjusting to reach the grasp? So some of this work has been done, but in a limited way. So one work has looked at understanding the effect of Ebbinghaus illusions on depth judgments, but using the flat disk. Okay, so not using three-dimensional disk, kind of replicating the Ebbinghaus illusion study, but in VR using the flat two-dimensional disks. And what they found is, yes, the Ebbinghaus illusion has similar effects as it does in the real world. And another study kind of looked at a fits tapping task on static 2D objects. And I say static meaning the Ebbinghaus illusion inducers did not change. So they were the same size throughout the entire task that they were using. And so what we were curious about was, okay, in the VR environment, beyond 2D disks, do you have this effect, one, with three-dimensional inducers? And then two, what happens if we dynamically change those inducers? So what if they appear or disappear in that path planning and action, actually performing that grasping task, while you're doing that, in changing the inducers, does that change your behavior? Does that change how you're interacting? And this is really important for 3D user interaction because one, if you kind of display some menu information around an object, or maybe you have a cluttered environment where you have objects around that can change our performance and how we're reaching to grasp various virtual objects in the environment. But on the flip side of that, if that does change our behavior, can we use that to design a 3D interaction technique to help improve how we might interact with objects at a distance, or how we might take advantage of interacting with objects and kind of shorthanding the interaction to where you don't have to reach the entire way. You can kind of reduce fatigue in that manner. So is there an effect at all? And so we conducted a study where we manipulated the inducers around the object, and we also manipulated the vision of your virtual hand, whether it was present or not. And we looked at whether the visual inducers, if they went away at the start of your reach to grasp behavior, or if we took them away at the end. And so just kind of want to show this video to kind of give an idea of some of the stimuli and the task in terms of reaching the grasp of the virtual object. So in this case, you can see the various inducers. So the large, and then the small had appeared just a minute ago. So here's the small inducers again around the object. And the idea was, so let me pause this for just a second. So in this, it may be hard to see, but there's a sphere here, a sphere here. These represent kind of the fingertips of where you're adjusting your grasp for the object itself. So in that case, as they're reaching to grasp, the objects appear at the end of that cycle, or they disappear at the end of that cycle. Okay. Okay, so I'm not going to go into too much of the details, but the idea is that what we found is that, one, we replicated the perception study in that the size of the object was perceived differently based on the inducers that surrounded the object. Okay, and but we did see some interesting effects on that planning and action phase when reaching to grasp that virtual object. So when they were reaching for the object, and so we thought, okay, if we have the inducers disappear, we thought, okay, the illusion or the idea of the illusion would maintain, and as you were reaching for the object, you would adjust accordingly at the end. And so what we found is that the illusion actually changed the way you adjusted your behavior and continued even beyond when the illusion disappeared. So that was an interesting finding. And then the inducers actually constrained the action as well. So if you imagine, okay, yeah, these inducers change your perception of the object, but what also happened was there was some object avoidance. So as they were kind of adjusting at the end of that reach to grasp cycle, they were trying to avoid the objects surrounding it. So that's interesting as well. So, you know, we might be able to use these for improving performance, but at the same time have to keep in mind that depending on the proximity of the inducers can change the way you manipulate or grasp the object as well. Okay, so in terms of looking at the display of the virtual hand, so the vision of the virtual hand is needed to help with that final adjustment step. And this just confirms existing literature that the presence of your virtual hand helps you to have better performance in the VR environment for those kinds of tasks. Okay, and then the last thing is that having that contextual target in order to give you some reference point is important as well. Okay, so going back to this idea of reaching to grasp, we want to know, okay, what are sort of some of the other things that we can do to change behavior? So if we're looking at this, we're changing that behavior for selection and that sort of thing. So we wanted to look at, well, how can we use perceptual illusions to change other forms of interaction, such as navigation? And so one of the other studies that we're working on is that, and this kind of started with how do you simulate navigating stairs using props and things like that. So the idea of navigating to a second story in VR typically is done through a virtual elevator or escalator or just teleportation. There's not many environments that look at, okay, what if we were going to simulate more real world stair navigation? And the purpose for that might be something like training applications, like if you were training for firefighter training and you had to kind of simulate some of that navigation, or an architectural walkthrough where you're interested in how your view movements kind of move through environment and change as you're kind of navigating the stairs up or down, maybe how the lighting changes in the environment as you're naturally walking through. And so one of the things that we're looking at is if we virtually adjust or virtually change some of the stimuli in the environment, how you're looking at the environment, while you're navigating the stairs horizontally, does that one give you a more of effect of moving up the stairs? And then two, we're also looking at how those various visual changes could give you the more sense of fatigue or more closer sense of fatigue to real stair navigation, again, for possibly training purposes. And then the third being that how does your view change in the environment as you're navigating those virtual stairs in that architectural walkthrough example that I gave you. So we're actually currently collecting data on this. So this is an ongoing study right now, in that we looked at, we're looking at 4 different virtual manipulations. One being just kind of setting your path, your view path, to be very similar to natural walking collected from natural walking data. But then we were also looking at other visual manipulations in terms of kind of changing your perception of your body movement. And in the data so far that we're seeing, in that virtual, in that change in virtual perception and how you're envisioning that your virtual knees are moving above or below in your gait, that you're going up and down in steps, actually in the real world changes your posture to be more similar to what you would have in the real world when you're navigating up and down the stairs. So we actually have different posture poses going when we're navigating up or down stairs. And so in one of our techniques, we're actually finding that people or participants don't realize that their posture is actually changing based on those visual perceptual changes in the environment. So in any case, that's just some of the initial data that we've seen so far. We're still collecting data on it. So we're interested to see what comes out when we finish the study. In terms of looking back at that, one of the other problems that I talked about, which is fatigue. So a number of work that some past work that I've done kind of helped look at reduced fatigue techniques and even some novel input devices. And so one of those is 3D touch. We developed to combat the problem of kind of when you walk into cave environments, your visual display is in front of you, and maybe you have 2 displays on either end, and you have a floor display. And aside from having maybe a joystick, there's not really anything you can leverage in the environment to interact more accurately. So the idea behind this device was you could now turn your body into a touch device, basically, or various props that you have with you, you could change, or you could actually do midair interaction as well, but combined with leveraging whatever physical you had in the environment, including your leg or your arm or whatever that may be. Something else that we looked at to reduce fatigue, I work with a kinesiologist who studies the human body movement and injuries and how people move in the environment in the real world. However, when he studies these environments, some of the sensing techniques in the real world are not feasible to do something in real-time sport games and things like that. So I'm wondering how we can track better movement outside the experimental lab. And so one of the ways, there are ways to track in the real world, but we wanted to look at how we could track real time, because in some of those ways that you can track in the real world are more video based and things like that. And so one way is to look at smart textiles and e-textiles. So that's certainly a viable solution. But I started to think about how you could do this without um, your clothing, in the sense that wearing it underneath your clothing or something like that. And so thinking about skin-worn tactile devices that you could wear underneath your clothing. And so these are just a few other solutions. And so then Kinetic Skin was a result of actually a cross-pollination of research that did with some folks in Atlas. Um, Clement Zhang was working on paper-based interfaces and how to um, create paper-based interfaces that, when you kind of bend them or flex them, would provide input into the virtual environment. So taking that idea and applying it to temporary tattoos, was able to kind of make it as a skin-worn, basically a skin-worn flex sensor that could provide input and track joint information into the environment. So let's see, we're kind of running out of time. So that's just kind of how it works. So I kind of want to show an early demo of this, where we can actually get relative information given that bend sensor. Okay. And what's really nice is that we could apply this to gestures in the environment, where you can actually do complex hand movements and be able to track those, as well as be able to do more finger-based and apply that to selection, rotation, manipulation, things like that. So this is just one example of using your finger to flex and rotate an object. Oops. And then this is an example of scaling an object using that relative motion. So this still is a project ongoing. And so some other projects working on develop some soft silicone-based devices. Something I'm working on right now at University of Wyoming is that one of the things with the Arapaho language is that they're realizing that the newer generation is kind of losing it a little bit and not learning it as easily. And so they're trying to look at new ways to help teach their children the Arapaho language, not necessarily for outside members, but for within their own. And so one of the things that we're looking at is, because the Arapaho language is very much a spatial language and tied to spatial locations and what's in the environment, is looking at, one, how can VR environments help to learn and practice the Arapaho language better than traditional methods. And another way that we're looking at is, can we use the spatial environment to help phonetically learn the Arapaho language a lot better? And so those are just a few of our ongoing projects. I would really like to take any of your questions. And again, that's just kind of an overview of some of the projects that I work on. And so I'm happy to talk about any of those more with any of you. So I'll open the floor, I guess, to the invisible people before me. I'll stop sharing. So maybe I'll ask a question if no one else has any questions. I'm curious because I don't know many of the people in here. Um, what are some of the things that you all do, or more broadly? Oh, great. Thank you, Brian.
Yeah, thanks for the talk. It's definitely interesting, but definitely outside my area of expertise. I tend to do stuff in kind of the intersection of programming language and security stuff.
Oh, cool. Well, cybersecurity is an interesting one for VR. And actually, working with Julia, um, we are looking at cybersecurity in VR from the perspective of, again, using visual illusions to help determine, okay, um, can we one, identify entry-level authentication given those illusions? So if I'm perceiving something in environment one way, but the bot might perceive it another. So for example, if you had an image of a sphere or multiple spheres, but it was just a flat 2D texture, the bot might look at the geometric objects and say, oh, there's no spheres in the environment, or maybe there's a deceptor sphere in the environment. And so the bot will select the sphere that's actually the geometric object. Whereas if we're rendering from a certain perspective into the environment, we might look at the 2D texture and it might appear to be three-dimensional to us. So we might say, oh yeah, that's a sphere over there. And that because of our perception, we can be maybe identified as human instead of a bot in that case.
Interesting. So like a CAPTCHA on steroids.
Yeah, well, CAPTCHA in the VR.
Yeah. Awesome. Maybe a question for you that's less related to your talk. So I'm also involved in helping with some of the undergrads who are going through their capstone projects right now, and a couple of them are tasked with doing making VR applications. Are there resources that you would recommend pointing them to within the Atlas Institute if they're interested in learning a little bit more about what you and other folks in the institute are doing and potentially incorporating that into some of their projects?
That's a great question. So one would be, I guess the resources of the Atlas website kind of show what kind of research is going on in the space. I know that this semester I'm teaching a course on introductory augmented reality and virtual reality. And next semester I'll be teaching a course on spatial user interfaces. And so I think um, that might be something in terms of, one, I'd be happy to talk with any of those students. In fact, one student group has already reached out to me to talk with me. But in terms of, I guess, hardware resources, I think kind of talking with um, those that manage the equipment spaces and things like that might be one option. But in any case, I mean, I'm happy to talk with any of the student groups and point them to online resources as well and things like that.
Perfect. Thanks, Amy. Yeah, I'll point them to this talk and then also to you if they have more questions and interest after that. So thanks.
Yeah, and you know what? Since consumer VR has become more affordable and you have the kind of growth of Unity and Unreal and A-Frame and all these different resources. There's a lot of learning material online to learn how to build VR environments and things like that. So there's a ton of information out there. Other questions or other areas of expertise in the room? VR work for the visually impaired. I have not done any work for the visually impaired. There is a number of research out there that has been done. However, I have done some work with brain-computer interfaces with the potential that individuals with physical disabilities could engage with and use the VR environments. And so one of the things that we were looking at was, okay, visual imagery is one way to train the brain-computer interface. So if I imagine motor movements, like, okay, if I imagine my left arm moving and then my right arm moving, I can pair them to actual input into the VR environment where I navigate left or steer left and steer right, respectively. So one thing that we were looking at was, okay, what else can we kind of take advantage of in terms of providing robust input? And in general, brain-computer interfaces are highly variable and things like that. But we were looking at, could you use selective listening to control or navigate spatially your steering? And so what I mean by that is, if audio stimuli was presented spatially on one side versus another side, and it has to be distinctly one side versus the other, so I'll explain in a minute why. If you were to actively listen to the audio stimuli on the left, then it would transfer to navigating or steering left in the virtual environment. And if you were to actively pay attention to the right stimuli, then you would actively navigate or steer right in the environment. And so one of the ways that we looked at dividing this, so we looked at audio stimuli that was actually the same stimuli on either side, and you had to pay attention to one side versus the other. So there was an effect that worked in the case that you could navigate left or right given this, but it wasn't as strong as something like, okay, we can differentiate language versus music. And so a lot better than a single stream of audio. And so if you had in your left ear an audiobook, for example, and in your right ear music, you could more easily pay attention to one versus the other. And it was a little more robust. And so one of the things that we were thinking about in terms of that is that we could expand the things that you could do within the environment. So then if you were using a listening technique for navigation, you could use the motor imagery technique to do other tasks in the environment. So you could actually separate those degrees of freedom, if you will, for brain-computer interfaces. So that was some past work I did. I've also done some work with a startup company where they looked at individuals with Parkinson's disease, where they, because of various tremors and how unpredictable they are, and maybe how intense they can be, it's difficult for those individuals to interact with touch-based displays, and touch-based displays are almost everywhere now. They're in the shopping that we're doing. They're in the checkout counter for checking in for a flight. You know, I'm sure you can think of some other really good examples as well. So the idea was to develop a stylus that would serve as a stabilizing mechanism to be able to identify or select things on a touch-based display. I know that's not really VR, but it does have spatial user interface application. And we looked at the stylus technique. We also looked at kind of using separated button for the action, because they could actually control pressing a button a lot better than controlling the spatial rotation of a stylus. So if they could narrow down the area that they want to click and then use the button to actually click, that made it a lot easier. And we did a study with individuals with Parkinson's, and it was really cool because somebody who mentioned that they used to be really good at drafting and drawing, and for their work they did a lot of that activity, and when this disease kind of took over, they are not able to do that at all anymore. And when they were using our device, they were able to kind of open up that and be able to do some tasks that they hadn't been able to do for a while. And so that's some of the work that I've done in that area. Other questions or? Yes, you're welcome.
All right, well, if we have no more questions, let's give our speaker a round of applause. And thank you so much for the wonderful talk.
Thank you for having me. Have a good rest of your day.